Today, on the course of Physics Basics, we are standing on week 2. Here, today, we are going to study about motion, force, momentum, and torque. Before going ahead, let's get into the recap. In the last session, we have covered Introduction to Physics, Units and Measurements, Scalar and Vector Quantities. What's on the plate today? On today, the table of contents as follows. Motion. Frame of reference. Motion with constant acceleration. Inertia. Newton's law of motion. Force. Types of forces. Momentum. Torque. The learning objectives of today's session will cover the concept of motion and rest, application of Newton's law of motion, application of different types of forces on a body, basic definition of momentum and torque, and how they are calculated and can be understood. Let's get started with motion. What is rest and what is motion? When a body is said to be at rest, let's get to know it with examples. When the position of the body does not change with time, it is called to be at rest. Examples: an apple lying on a table. It's not changing its position with the time. Suppose at time t equal to 0, it is at rest, and at time t equal to 5 seconds, it would be at the same position. Apple would not change its position by itself. So, the apple is lying on a table and said to be at rest. The second example could be a flower pot on the ground. Similarly, as of apple, flower pot couldn't change its position by itself with the time. Thus, the flower pot is said to be at rest. When is a body is said to be at motion? When the position of the body changes with time, it is said to be in motion. It could be understood with the examples. A person playing cricket. Here, we can see that as the ball comes closer to the batsman reacts accordingly for the shot. Thus, its body is said to be in motion. Another example from which we can study the body at motion is a moving truck. We can see here the truck is moving in forward direction. Thus, it is said to be in motion. Note: the term motion depends on the body under consideration and the viewer. Like suppose here, the driver is in the rest relative to the truck as he is sitting inside the truck. Or we can also say that the truck and its driver are both in motion relative to the road. I mean to say that if a person is standing on the road, he would say that both driver and the truck is moving in forward direction. Or the driver himself is the observer, then he would say, the truck is moving, I am at rest. The next thing we are going to study is frame of reference. Frame of reference is required for locating the position of any object or particle. Example: with respect to the road, the car moves and cycle does not. It means the observer is standing on the road and talking about a frame of reference called road, where the car is moving on the road and cycle is still. This infers that road is the frame of reference. Frame of reference. The next thing we are going to study on frame of reference is motion in a straight line. Consider an object traveling at a distance x at a time t. Then velocity of the object would be written as v is equals to dx by dt. Let's get to know this example with the help of figure. This is an object at time t is equals to 0. It is at rest. Thus, the distance is equals to 0. At time t, the object travels a distance x. Therefore, the velocity of the object can be written as dx by dt. If dx by dt is positive, the direction will be in the positive x-axis. Here is the coordinate axis given. Similarly, if dx by dt is negative, the direction will be in negative x-axis. Further, we can also find out about the acceleration, as acceleration is given by the formula dv by dt, that is change in velocity with respect to time. If dv by dt is positive, the acceleration will be in positive x-axis as given in the coordinate axis, positive x-axis. Similarly, if dv by dt is negative, the acceleration will be in negative x-axis. The next thing we are going to learn is motion with constant acceleration. Motion with constant acceleration. Consider an object. Let the object be a ball that has been traveling in a straight line with constant acceleration. Thus, since the ball is at rest at time t is equals to 0, let's consider its velocity u. As the ball moves in a straight line with constant acceleration, it would move to a different point with a velocity v. The time taken to reach the velocity v from u, it would be t. Thus, at time t is equals to 0, velocity was u. At time t is equals to t, velocity is v. Here, we have to assume that the acceleration is constant. Thus, as the acceleration along the straight line is constant, acceleration can be written as dv by dt, where acceleration is actually change of velocity with respect to time. As we have seen earlier that initial velocity of the ball or of the object was u, and the final velocity of the object or ball was v. Similarly, the time has also been changed there. Since the ball was at time is equals to 0, to attain the velocity from u to v, the time taken was t. Therefore, acceleration here is written as dv by dt. Further, by applying the cross product rule, dv is equals to a dt. Since the initial velocity was u and the final velocity was v, thus we have to integrate dv by from u to v, and ADT would also be integrated in the manner such that the initial time would be taken as 0 and the final time to achieve the velocity v would be t. Thus, dv would be integrated from u to v is equals to ADT to be integrated from 0 to t. Applying integration rules, this can be written as v from u to v is equals to a. As a constant, it would be out of the brackets, and t would be written as big bracket t from 0 to the time t, where 0 is the initial time, t is the final time required to attain the velocity v from u. Thus, v minus u is equals to at minus 0, where a is acceleration and is constant. Applying integration rules here, t could be written, t when integrated from 0 to t can be written as t minus 0. Thus, v minus u, the LHS would be same as the last. V minus u is equals to a t minus a 0, which is actually 0. So RHS would be directly written to only a t. Thus, the equation written here is v minus u is equals to at. This can also be written as v is equals to u plus at. Let's consider this as equation 1. Getting further, we need to first understand the difference between distance and displacement. Let's consider an object, that is a ball, that does two movements simultaneously. The first movement would be from here to this point. The second movement would be from this point to return back to this point. All the motions would be done on a straight path, but in different directions. The movement 1 would be in positive direction. The movement 2 would be in negative direction. As we can see, at movement 1, the ball moves from x is equals to 0 to x is equals to 5 meter. Thus, the distance travel at movement 1 is 5 meters. At second step, ball moves to point this. That is, movement 2 is from time t dash to t. So, the distance travel in movement 2 is just 2 meters, since the position of the ball here is 3 meters only. So, the ball was at rest. So, at time t is equals to 0, x is equals to 0. Then ball moved to point this, where at time t dash, the distance x is equals to 5 meter. Further, the ball returned back to some point, and where the time required to go back is at time equals to t, the distance travel was 3 meters. Thus, the net distance traveled by the ball is 5 meters plus 3 meters is equals to 8 meters. But if we talk about the displacement is the shortest distance travel. Thus, the shortest distance travel from point 1 to the final point is just 2 meters, since 3 meters has been traveled from here to here. The 2 meter has been traveled from here to here. Thus, the displacement would be just 2 meters. The distance would be 8 meters. 5 plus 3, 8. After knowing the difference between distance and displacement, let's get further. Here, x is actually displacement, not distance. It was important to understand the difference between distance and displacement for these formulas. As we have learned earlier in equation 1, v is equals to u plus at, and v was the final velocity, where we also know that the formula of velocity is distance upon time, or displacement upon time, that is dx by dt. Change in distance with respect to time is called velocity. Thus, v can be written as dx by dt is equals to u plus at. Multiplying u plus at by dt, we can write it as dx is equals to u plus at dt. As we know that the distance traveled was from point 0 to x. Thus, dx would be integrated from lower limit 0 to upper limit x. And the RHS of the equation u plus at dt would be integrated from 0 to t, because at time t is equals to 0, the body was at rest and at point 0. But as the ball moves forward, at time t is equals to 0, the distance traveled by the ball is x. Applying integration rules, we can write as x is x in the big bracket with limits 0 to x is equals to u dt and at dt. This has been written after the multiplication of u with dt and at with dt, where a is acceleration, t is time, u is the initial velocity, and dt is change of time. Thus, applying integration on each of the RHS points, u dt can be written as u dt integration from lower limit 0 to upper limit t, plus integration of at dt would be similar from lower limit 0 to upper limit t. Thus, applying integration rules here in this equation, we can summarize this equation as x is equals to ut plus half at square, where the x, u, t, a have their usual meanings as x is displacement, u is initial velocity of the object, t is the time required to achieve the velocity v, or to time required to get into the position x, plus half at square was a is acceleration of the body and t is the time required to achieve the velocity v or to reach at the point x. This whole equation is written as equation 2. Further, for getting ahead, we already know that equation 1 was v is equals to u plus at. After squaring the equation 1, we would get v square is equals to u plus at square. The LHS of v square would be v square only, but we can see here a mathematical formula applying. Mathematical formula we have studied in basic classes is a plus b's whole square, the whole square of a plus b, and that is actually a square plus b square plus 2ab. So we are going to apply the same mathematical formula here, where a is equals to u and b is equals to at. Therefore, the RHS can be written as u square plus a square t square plus 2u at. This complete equation could be read as v square is equals to u square plus 2u at plus a square t square. The LHS could be written as same, where RHS can be also written as u square plus 2a, where we have taken the common 2a from the above equation. Thus, u square plus 2a to be multiplied by ut plus half at square. Can we see something similar that we have studied in the previous slide? Ut plus half at square. Yes, this was equation 2. and ut was half at square was equals to x. Therefore, putting equation 2 here, we could simplify this complete equation by writing it as v square is equals to u square plus 2ax, or v square minus u square is equals to 2ax. This we can write it as equation 3. Thus, as a result, we can see that for solving a problem of straight line motion with a constant acceleration, the following equations can be of use. The equations are equation 1, v is equals to u plus at. Equation 2, x is equals to ut plus half at square. The third equation is v square minus u square is equals to 2ax, where all the symbols have their usual meanings, like v is equals to final velocity of the object, u is equals to initial velocity of the object, a is equals to acceleration attained by the object, t is equals to time required to reach at the point x or time required to reach at the velocity v. And what is x? X is actually the displacement. As we have learned earlier, the difference between distance and displacement. Displacement is the shortest distance traveled,